Passive computing is reaching its expiration date. The cycle of launching an application, clicking, and typing is over. For the last several years, artificial intelligence has functioned as a simple transaction. You provide a prompt, and the model returns a block of text. That transaction has evolved into an active loop. This is the agentic model, software that executes multi-step work without waiting for continuous human instruction. This software behaves like a reasoning worker. At its center is a large language model acting as the brain. This brain operates within a software harness, orchestrating memory and connecting to tools like browsers, spreadsheets, and databases. Every step requires routing context. The agent observes, plans, calls tools, and evaluates results before proceeding. Modern software has evolved into an active reasoning force. This change renders the physical hardware built for passive tools structurally obsolete. Agentic software is disaggregated. It separates the thinking from the doing in a way traditional architectures weren't designed to handle. Hardware must be rebuilt to serve the dominant software model of its time. 30 years ago, the rise of the graphical user interface forced a complete reconstruction of PC architecture. Today, when an agent switches contexts or accesses a tool, it creates a massive data traffic jam across standard cloud architectures. These models have outgrown the limits of a single machine. Processing a single agent now requires compute power to be distributed across multiple server racks. To run these agents without a total collapse in performance, NVIDIA had to rebuild the computer from the microprocessor up. Most industry analysis assumes that AI performance is exclusively a function of GPU scaling. However, in a tool call workflow, the GPU, the model, reaches a decision and then must hand the actual execution task back to the CPU. Standard x86 CPUs were optimized for humans. They slice up cores to be rented by the hour, operating at human-scale latency. Agents operate in nanoseconds. If the CPU lags during execution, the massively expensive GPU sits idle, wasting the most valuable resource in the data center. The NVIDIA Vera CPU solves this orchestration bottleneck. It is a processor built for the specific demands of the agentic loop. Vera prioritizes single-threaded performance, executing 10 instructions per clock cycle to minimize latency for branch-heavy runtimes. For massive KV caching, Vera delivers 1.2 terabytes per second of memory bandwidth. A monolithic mesh fabric allows all 88 cores to communicate without chiplet latency penalties. These architectural shifts produce immediate results. In high-stakes environments like the New York Stock Exchange, Vera is 6 times faster than traditional CPUs. The CPU now functions as the high-speed conductor for the GPU orchestra. Individual chips are only part of the solution. Agents require hardware that is distributed yet tightly coupled at a system level. Vera Rubin is a multi-rack, pod-scale supercomputer specifically designed to run these distributed, tightly coupled agentic systems. Inside the rack, work is divided by specialty. Blackwell GPUs handle reasoning, prompt processing, and context understanding. Hundreds of Vera CPUs operate in the same rack to manage tool calls and memory shuffling in real time. Bluefield DPUs manage storage processing and provide security directly in the silicon. This hardware-level security is a requirement. Because enterprise agent models are high-value proprietary assets, they must remain encrypted while in use via confidential computing. To unify these components, NVIDIA utilized cableless PCB midplanes and liquid-cooled busbars carrying 5,000 amps of current. The Vera Rubin rack collapses millions of disaggregated components into a single processor tailored for the agentic loop. Scaling these racks leads to the gigawatt-scale data center. In this environment, compute is synonymous with revenue. These factories convert electricity into tokens. When agents use tokens to verify designs or write software, they drive GDP growth. Physical power is the ultimate constraint on economic output. Maximizing token output requires co-designing the factory for efficiency, from silicon-level wattage control to direct liquid cooling. To mitigate capital risk, operators use digital twins in NVIDIA's Omniverse to simulate every aspect of power and cooling before breaking ground on the site. NVIDIA now engineers the full-stack factories that manufacture digital intelligence. The agentic software loop is not confined to the cloud, it scales down to the edge. The RTX Spark architecture represents the first total reconstruction of the personal computer in 40 years. This board fuses a custom 20-core Grace CPU with the Blackwell GPU architecture. It is designed to run sandboxed personal AIs locally, allowing agents to manage workflows without the latency or privacy risks of external servers. The PC acts as an autonomous assistant, running continuously in the background. The final frontier brings this reasoning into the physical world through autonomous robotics. Physical AI is currently bottlenecked by a lack of data. While text is abundant on the internet, first-person training data for robots is scarce. Cosmos 3 is a foundation model designed explicitly to overcome this data scarcity. As a world model, Cosmos 3 generates physics-accurate synthetic video that mimics reality. This uses massive compute power to simulate infinite training scenarios, creating the data required to develop reliable robotic policies. By applying the agentic pattern to robotics, physical machines can observe, reason, and act in the real world. NVIDIA's hardware roadmap now spans from consumer laptops to humanoid robots to gigawatt factories. Every one of these machines is built to serve the agent. NVIDIA now architects the autonomous operating system, providing the infrastructure for a massive expansion in productivity.